All right, so get this. What if the heart of transformer models, the attention mechanism, is actually kind of lazy? Like, not all those layers are actually pulling their weight.
Right.
And researchers are finding ways to actually give LLMs a performance boost by strategically, slimming them down.
Yeah, it's pretty wild.
It is, right?
Yeah.
Like you're probably familiar with the idea that bigger isn't always better.
Of course.
And this deep dive is going to take us right into the guts of cutting-edge AI efficiency research.
I love it.
We're talking about this paper exploring a fascinating concept.
Okay.
Dropping specific parts of LLMs to make them faster and less memory hungry without sacrificing much accuracy.
Very cool.
So hold on to your hats, because we're about to explore which parts of these models are truly essential.
Okay.
And which ones we can just toss out like last week's leftovers.
Like last week's leftovers, I love that.
Right.
Yeah.
Okay, so you're probably familiar with the idea that these models are getting bigger and bigger. And that comes with some serious costs in terms of computing power and memory.
Oh, yeah, for sure. I mean, we've already seen some attempts to address this with things like quantization and pruning.
Right.
But this research takes a totally different approach.
It does. And the paper we're unpacking today, it really gets into the nitty-gritty of how they're doing this.
Okay.
It's called What Matters in Transformers. Not all attention is needed.
Catchy title.
And as the title suggests, it's challenging some fundamental assumptions about how these models actually work.
Yeah. And before we get too deep into the weeds, maybe just a super quick recap of how transformers are actually structured.
Yeah, that's a good idea.
Just to make sure we're all on the same page here.
Yeah.
So you can think of it like a stack of building blocks.
Right.
And each block is made up of attention layers and MLP layers.
Gotcha.
And, for a long time, the attention layers, they've been considered the superstars, the part of the model that allows it to understand relationships between different parts of the input data, like, words in a sentence. But this research suggests that maybe we've been giving attention a bit too much credit.
Okay, I like it.
So the researchers, they explored 3 different dropping techniques to see if they could get rid of certain parts of the model without hurting its performance.
Gotcha.
So the first one, block drop, that's the most aggressive.
Okay.
They literally just chucked out entire blocks of the model to see what would happen.
Wow. Okay, so that seems a little extreme.
It is.
Like performing surgery with a chainsaw?
Yeah, and it definitely had its limitations.
Yeah.
But it helped them start to figure out which blocks were really contributing and which ones were just kind of along for the ride.
Interesting. Okay, so what about the other techniques?
Okay, so the next one is called MLP drop.
ML2 drop.
This one is a bit more refined.
Okay.
Instead of dropping whole blocks, they targeted the MLP layers and a related component called layer norm.
Okay.
It's a kind of normalization process.
Okay.
But, the technical details aren't super important here.
Gotcha. So they're basically getting more specific with what they're cutting out.
Exactly.
But I'm guessing the real star of the show is the third technique, right?
You got it.
Okay.
This one is called attention drop.
Attention drop.
And this is where things get really interesting.
Okay.
So the researchers figured out a way to actually measure the importance of each attention layer in the model.
Wow.
And what they found was pretty shocking. A lot of them could be dropped with almost no impact on performance.
Wait, seriously, we can just ditch a bunch of those attention layers?
That's what the research suggests.
The things that supposedly make transformers so special?
Yeah, and they weren't just guessing.
Okay.
They developed this metric called the speed-up degradation ratio, or SDR,
Okay.
to measure the trade-off between making the model faster and any loss in accuracy.
Okay.
And attention drop had incredibly low SDR values, meaning it's a really efficient way to slim down these models.
Wow. Okay.
Yeah, pretty wild, right?
Yeah.
Makes you wonder if we've been overbuilding these things all along.
Right. Like, what if we've been doing too much?
Yeah, it's amazing how this research forces us to kind of, reconsider that whole bigger is better mindset
Totally.
that's dominated AI development for so long.
Okay, so let's talk about the results.
Okay.
What did the researchers actually find when they started dropping these attention layers?
Well, one of the most surprising things was just how consistent their findings were across different model sizes.
Okay.
So they tested this on everything from smaller models like Llama 213B
Right.
and Mistral 7B all the way up to the massive Llama 270B.
Wow.
And that pattern held true.
I remember reading that and thinking, there's no way they can just drop a ton of attention layers in a giant model like that and not see a performance hit.
Right. You'd think those massive models would be, meticulously optimized with
No.
every layer carefully tuned.
Yeah.
But the data clearly shows that even these behemoths have a lot of room for trimming.
So imagine you're working with one of these giant LLMs.
Yeah.
Suddenly, you could potentially cut its memory usage and computational demands in half.
Right.
Without sacrificing performance.
Exactly. That's huge for anyone who's actually working with these models. It
Right.
can make them so much more, accessible and practical to use.
Okay, so let's dive into the aha moment here.
Right.
What are the big takeaways from this research?
Well, first of all, it completely flips the script on how we think about attention in transformers.
Okay.
It's not that attention isn't important.
Right.
It's clearly not as, indispensable as we once thought.
So what does this mean for the future of LLMs? Are we going to see a shift towards smaller, more efficient models?
I think it's definitely a possibility.
Yeah.
I mean, why waste resources on a massive model when a smaller, leaner one can do the job just as well?
Right.
This research opens up a whole new avenue for optimizing LLMs, both in terms of how we design them and how we train them.
And this could have a ripple effect throughout the entire AI landscape.
For sure.
Imagine the potential for LLMs in fields like medicine,
Yeah.
education, and even art, if we can make them more accessible and less computationally demanding.
Absolutely. Think about being able to run sophisticated AI models on devices like smartphones.
Right.
Or even embedded systems. The possibilities are pretty mind-blowing.
This feels like a paradigm shift.
Yeah.
A move away from the bigger is better philosophy.
Right.
And towards a more nuanced understanding of what truly drives performance in these models.
And it's a great example of how research can challenge our assumptions and lead to breakthroughs that have the potential to, reshape entire industries.
But let's not get ahead of ourselves.
Okay.
Are there any limitations to this research?
Yeah.
Anything we should be cautious about?
That's a great question. It's important to remember that this is still a relatively new area of research.
Okay.
There's a lot more work to be done to fully understand the implications of attention redundancy and how to best leverage it.
So what are some of the big questions that still need to be answered?
Well, for one thing, we need to explore whether these findings apply to other types of transformer models.
Okay.
So right now, the research has focused mainly on LLMs, but transformers are used in a wide range of AI applications, from image recognition to machine translation.
So it's possible that this attention redundancy could be a more widespread phenomenon.
Exactly. It's like we've discovered this new principle of efficiency,
Right.
and now we need to see how far it extends.
Well.
Another big question is whether we can actually retrain these pruned models to achieve even better performance.
Gotcha.
So right now, these dropping techniques are applied after a model has already been trained.
So it's like a quick fix, a way to make existing models more efficient.
Right.
But what if we could bake this knowledge into the training process itself?
Exactly. If we could train models from scratch with fewer attention layers, we might be able to achieve even greater efficiency and performance.
Okay, so there's clearly a lot more to explore here. But this research feels like a major step toward a more efficient and accessible future for AI.
For sure.
It's like we've cracked open a door to a whole new world of possibilities.
I couldn't agree more. And who knows what other hidden efficiencies might be lurking within these models just waiting to be discovered.
Right.
It's an exciting time to be working in this field.
It really is.
Yeah.
Well, before we wrap things up, let's bring it back to our listener.
Of course.
Like we're standing at the edge of a whole new frontier in AI.
And the most exciting part is we don't even know what's out there yet.
Exactly. It's a constant process of discovery and innovation.
Yeah.
But speaking of discovery, one thing that really struck me about this research was that they found these attention redundancies throughout the entire training process.
That's right. It wasn't just a matter of, trimming down a finished model.
Right.
It seems like these redundancies are kind of baked into the very way we're training these models.
Which makes you wonder if there's a more efficient approach to training from the ground up. Like, what if we could build these smaller, more efficient models without having to prune them later on?
That's a really interesting question. And it's definitely something researchers are exploring.
Yeah.
Imagine being able to train a model that's already optimized for performance and efficiency from the start.
Right.
It could significantly reduce the computational costs and time involved in developing new AI applications.
And that could open up a whole new world of possibilities for using AI in fields that are currently limited by computational resources.
For sure.
Like, imagine being able to run sophisticated AI models on devices with limited processing power, like mobile phones or even tiny sensors.
Exactly.
Yeah.
It could revolutionize how we interact with technology and how we use AI to solve real-world problems.
So as we wrap up this deep dive, I want to leave our listener with a sense of optimism and excitement about the future of AI.
Yeah.
This research shows that we're still in the early stages of understanding these powerful models, and there's so much more to discover.
I completely agree. It's an incredibly dynamic field, and the pace of innovation is just accelerating. Who knows what breakthroughs are just around the corner?
And the best part is that these advancements have the potential to benefit everyone.
Right.
As AI becomes more efficient and accessible, it can be used to address challenges in healthcare, education, sustainability, and countless other areas.
It's a reminder that AI isn't just about building bigger and more complex models.
Right.
It's about finding smarter, more efficient ways to use these tools to solve real-world problems and improve people's lives.
Well said. And on that note, I think it's time to wrap up this deep dive.
Okay.
We hope you've enjoyed this exploration of attention, redundancy, and transformer models.
It's been a pleasure.
And remember, the world of AI is constantly evolving.
It is.
So keep learning, keep exploring, and keep asking questions.
Couldn't agree more.
Until next time.